Okay, in this video we're going to explore the physical properties of enantiomers, and we're going to look at molecules that have multiple chiral centers in them. First of all, two enantiomers have incredibly similar physical properties. They're going to have identical melting points, identical boiling points, identical densities, identical refractive indexes. They're going to be the same color. They're obviously going to have the same molecular weight. They're just really not going to be very different in their physical properties. The only physical property where they're really different is how they affect plane polarized light. So we've already discussed that with the Pasteur experiment. One, they have equal but opposite effects on their ability to change the orientation direction of plane polarized light, and we saw how that property, which we call the specific rotation, is one way that you characterize enantiomers. Okay, another place where enantiomers will also differ is in their interactions with other optically active substances. Okay, and we'll see some examples of that. I should have put another one here, but they're also going to be the same in their interaction with optically inactive substances. Okay, because of these properties, you really cannot create optically active material from optically inactive starting materials. Okay, and we'll look at some implications of that. Obviously, there's a lot of chiral things. How do they become chiral to begin with? There's no really good scientific explanation, but it probably relates to the fact that a lot of natural phenomena are actually chiral events, like the fact that the Earth is turning so that the sun rises in the east is a chiral event. Low pressure systems and weather rotate, I think, counterclockwise, and high pressure rotates clockwise. All of these are natural phenomena that are chiral. Probably the most obvious one is if you flush a toilet and watch the water go out, it always goes out, I think, in a clockwise direction. Maybe I'm wrong about that, but if you flush a toilet in the southern hemisphere, it has the opposite orientation. So there's a chiral event right there. Here, of course, if you've watched The Simpsons, you know that Bart actually tricked some Australian kid into doing this investigation, and here he is about to get the royal butt kicking, I guess, corporal punishment for his misdeed. Okay, all right. So let's look at some of the implications. Of course, most of you probably are aware that the proteins and carbohydrates and various other things in our bodies are chiral molecules. So we are just loaded with chiral molecules. And we see enantiomers differently. So if you ask, do two enantiomers smell the same? Actually, a lot of times they don't. Here's a good example of this. This molecule right here, carvone. Okay. R-carvone is the essence of spearmint oil. S-carvone is the essence of caraway seeds and dill seeds. These taste very different, so our perception of these two enantiomeric compounds is actually quite different. Many pharmaceuticals are also chiral molecules, and their enantiomers have different pharmacological properties. For instance, S-ibuprofen is a pain reliever. R-ibuprofen is not. There is an enzyme that causes the R and S interconversion, but it was thought for many years that if you can perfect a cheap synthesis of the purely S ibuprofen, you can cut the dosage down by 50%, and that would decrease some of the side effects like stomach bleeding and other things associated with excessive use of ibuprofen. Okay, methamphetamine is also a chiral substance. Here's a interesting thing. If you ever watch the TV show Breaking Bad, they started talking about chirality, but they didn't really gauge it properly, I don't think. So in Sudafed, which is the precursor to amphetamine in the early episodes, what they do there is they just sort of just get rid of that OH group right there with phosphorus, which you get from match heads, and HCl. And because Sudafed is a naturally derived compound, it exists as a single enantiomer. And when all you do is you just knock out that OH group, your methamphetamine is going to be the pure R enantiomer. Okay. However, in later episodes, after he perfects a synthesis from simple ingredients that are not Sudafed, he makes it from this compound, phenylacetone and methylamine. If you've watched that show, you'll hear it mispronounced as methylamine, but no real chemist would pronounce it any way except methylamine. However, the methamphetamine that you get this way has to be racemic, so I'm not sure that the stuff that made the hero sort of the show, Heisenberg, the real king of methamphetamine, I'm not sure his stuff seems like it would not be quite as potent because it's a racemic mixture, and whereas the stuff derived from Sudafed would be only the correct enantiomer. Okay, let's look at reactions that create chirality. Now we said that you cannot create optically active material from optically inactive substance. But here, look what we have. We have 1-butene. No chiral centers in 1-butene. HBr, obviously not a chiral compound, but they come together to make a chiral compound. But the deal is we didn't say you couldn't create chiral material. We said you couldn't create optically active material. So of course, things that are not chiral are not going to be optically active, so our two starting materials are optically inactive. Therefore, our product has to be optically inactive. So it's optically inactive but chiral. That means that what we produce here is a racemic mixture. Okay. All right, so let's look at what we're doing here in this reaction. All right, we're reacting 1-butene with HBr, and remember that these two carbons here are an ethyl group. Just to simplify the structure, I'm going to abbreviate that ET. Okay, so it's going to be protonated. Our CH2 becomes a CH3, and we still don't have any chirality yet. Our chirality comes from whether bromine decides to attack from the top face, like here, and produce the S enantiomer, or does it attack from the bottom face, down here, to produce the R enantiomer? Well, in a totally achiral environment, there's a 50-50 chance of this happening. There's nothing differentiating one face of this molecule from the other. Thus, it's doomed to produce the 1-to-1 R to S mixture, or the racemic mixture. Okay, chirality has a lot of interesting implications for the origin of life. Okay, so this is actually a Nobel Prize winning experiment from many years ago. Miller and Urey did an electrical discharge in a simulated primitive Earth atmosphere of methane, water, hydrogen, and ammonia, and were able to generate many of the alpha amino acids, which are protein building blocks. But from their experiment, you only get the racemic material. So one of the big mysteries in the origin of life is how did all of these things become chiral? Science really does not have a or a universally accepted explanation for that at this point. So let's say if you're an alien and you're landing on a new planet, this is not really the right thing to say. What you really want to ask these people is the most common sugar, glucose. Does it rotate plus or does it rotate minus on this planet? So Roger here is enjoying a donut, but there's only a 50% chance that he could ever get anything out of that donut because of the planet that life originated, or how life originated on his planet only had a 50 chance of selecting either enantiomeric pair. So if had they accepted the wrong one, there would be he could get no calories from the glucose, and so if you ever visit another planet like that, I mean this is kind of fantasy here, but you'll have to bring your own food supply unless you're already sure that the biomolecules on that other planet originated the same way they did on Earth. There's only a 50% chance of that. Okay, all right. Let's look at attempts to create chirality. We're really not creating chirality here, but this is the 2001 Nobel Prize in Chemistry. It went to these investigators here for the development of asymmetric catalysis, and what they found is that they could take a very small amount of chiral material, or optically active material, which tends to be quite expensive, and they're able to just dump that into a reaction. And here this molecule here called diisopropyl tartrate makes a complex with this, which is actually a Lewis acid catalyst. So all it takes is just a small amount of this catalyst to produce large amounts of this chiral material here. So from this enantiomer you get only the S epoxide. This is an alternate to the peroxy acid method for generating epoxides, but if you use this method you can generate large enantiomeric excesses. Okay, this is the anti-Parkinson's drug L-DOPA right here, and the asymmetric catalysis was really perfected on a large scale by Monsanto in their efforts to develop a cheap synthesis of L-DOPA. And what they found is that they can take this flat molecule here that has no chirality and treat it with hydrogen and this chiral rhodium catalyst, and this will generate specifically the L enantiomer of this compound. Okay, and interestingly here, this is a chiral molecule, but you don't really see a tetrahedral carbon with 4 different things attached to it. Okay, because you can't put this hydrogen and this hydrogen in the same place at the same time. This molecule adopts a shape that's kind of like a screw, okay, or like a helix. So for that reason, it also serves as a chiral molecule. This is not the most common type of chirality, but it is a source of chiral molecules. This is called a tropoisomerism, and it has been used a lot in the development of novel ligands for this asymmetric catalysis reaction. Okay, let's look at molecules that have multiple stereocenters here, and we'll look at first this molecule. Let's see, how do we call this? Okay, 2R bromo 3S chlorobutane. Okay. All right, so that's molecule A. Okay. And if we look at the top, if we do the RS assignment, bromine's 1, remainder of the molecule is 2, methyl's 3, hydrogen's 4. It's already to the back, so we can see that the top is R, the bottom. Chlorine's 1, remainder of the molecule is 2 for the stereocenters, and methyl is 3 again, and the bottom is S. Okay? In the mirror, A sees B. Okay? And we say that A and B, these are mirror image isomers, and thus they're enantiomers. Okay? And what we see here is that when we go from A to B, position 2 goes from being R to S, position 3 goes from being S to R. And this is an important way, this is the most important definition of enantiomers. This is the one that'll probably serve you the best. Enantiomers have opposite configurations at every chiral center. Alright, so let's look at how does what if we change one of the stereocenters but leave the other one alone? So I'm going to change the bottom one, and we're going to generate this new molecule C. Okay? Alright, if we look at C, what we see here is that we have the same configuration at C2, but the opposite configuration at C3. Okay. A and C are a different type of stereoisomer. These are called diastereomers. A and C are diastereomers, or diastereoisomers, I guess is the official term, but it's too many syllables, so most people shorten it to diastereomers. Okay, in the mirror, C sees molecule D. Okay, and again we see this opposite relationship at every chiral center when we have enantiomers. C and D, oops, sorry, that second arrow should have gone there, sorry. C and D are also enantiomers, okay? And again, they have the opposite configuration at every chiral center. Thus, they're enantiomers. Okay, if we look at A, B, C, and D, we also have a lot of diastereomeric pairs, okay? A and C are diastereomers. B and C are diastereomers. Diastereomers have the opposite configuration at some. Okay, let's spell the word some correctly, but not all of the chiral centers. Some but not all is the definition of diastereomers. So A and C, B and C, A and D, B and D. These are all compounds that are in a diastereomeric relationship. Notice that when we had two stereocenters, two chiral centers, we had 4 possible stereoisomers. Okay, and this is an important equation. The maximum number of stereoisomers equals 2 to the n, where n is the number of chiral centers. And among these chiral centers, half of them will be diastereomers. So there'll be 2 to the n minus 1 diastereomers, each of which can be a pair of enantiomers. And we'll see why being diastereomers is a bigger deal than being enantiomers a little bit later in this video. Okay, we're going to make a subtle change now. We're going to make it so that C2 and C3 have identical chiral centers. We're going to change the chlorine at C3 into a bromine. Alright, so if we look now at, do the same analysis, A in the mirror sees B. However, A and B are not enantiomers now. They're actually identical compounds. There's a plane of symmetry within this molecule right here. What you see is everything above and below the plane reflects perfectly. Okay, so we refer to AB, doesn't matter because they're the same molecule, as a meso compound. Okay, a meso compound has chiral centers, but is not chiral due to a plane of symmetry within the molecule. It's actually half of the molecule is a racemic mixture of itself. Okay, that's the one way of looking at a meso compound. There's also some ambiguity in the numbering system, right? What's correct here? Who knows? Okay, they're basically the same numbering system. Okay, they're both technically correct within the IUPAC system. So there's this ambiguity that's kind of the source of it. All right, let's do the same thing we did previously. Let's make the bottom chiral center different. Okay, so this is now the 2R3R compound. Okay. In the mirror, this compound, C, sees the 2S3S compound, and this is the enantiomer. Again, you see the opposite relationship at every single chiral center in these two enantiomers. So C and D are enantiomers, and there's no plane of symmetry within this molecule. No matter what you do here, hydrogens line up across the plane, but bromine sees methyl and bromine sees methyl here. So that's not a plane of symmetry. The plane of symmetry we had in the AB system up there does not exist in the CD system. Okay? So therefore, C and D are actually, these are chiral molecules. Okay? They're not meso. Okay? If we look at the AB system, how does it relate to the C and D system? Well, A and C are diastereomers, A and D are diastereomers, A and B, since they're identical compounds, it would be moot to do the same comparison with B. But this is a common situation where you have the possibility of meso compounds. Not all of them are meso. Okay, so C and D are often referred to as the DL diastereomer. It's the one that can exist as a pair of enantiomers, and A, or again B, they're not really different, is referred to as the mesodiastereomer, the one that's not chiral. Okay, a mesodiastereomer exists if the molecule is palindromic, meaning that it reads the same way left to right as it does right to left. If you have this situation, you have the possibility that at least one of the diastereomers of this compound could be a meso compound. Okay. And another way of looking at it, I say it's palindromic. It reads the same left to right as right to left. You can also say that when you draw the two-dimensional structure, there's a plane of symmetry. Okay, so this compound here, heptane 3,5-diol, again, no matter how you number it, it wouldn't be different, right? It's the same, okay? And you can also see that you have a sort of a plane of symmetry right there. All right, heptane 2,6-diol also has this plane of symmetry, or palindromic, and one of the diastereomers of heptane 2,6-diol would also be Meso. Here we have 3 chiral centers, and one of the isomers of, actually 2 of the diastereomers of this compound are actually Meso compounds. All right, the molecule on the far right, however, there is no possibility for this to be a Meso, okay? If you had to assign a proper IUPAC numbering system, you'd have to number from the right, and this would be heptane 2,3,6-triol. There's no confusion, and you can't draw any point here where there's a plane of symmetry in the two-dimensional structure. Okay, cyclic compounds can also have mesoforms. Okay, we remember a few weeks ago we referred to the cis and trans cycloalkanes. In this case, they're not cycloalkanes, they're cyclic alcohols, but we refer to them as being diastereomers, and here you see why. They're different at some but not all of the chiral centers. Same. Opposite. Thus, they're diastereomers. Okay, this molecule, of course, the cis compound has a plane of symmetry, like here, right? So the cis is actually the meso. It could be called the meso as well as the cis. Whereas the trans, there is no plane of symmetry. There's an axis of symmetry, but there's no plane. So it can have an axis and still be chiral. This compound here, there's a plane of symmetry right there. This is meso. This is meso too. The methyl will be up. But if we take the hydroxys and make one of them opposite, of course, this plane of symmetry no longer exists, and this is a chiral or a DL, diastereomer. Okay, so here's an exercise for you. Just circle the or just say yes or no for whether each of these compounds can have a mesodiastereomer available to them. Okay, and I'll go through this, and you should pause it and do it, but I'll go through the answers. First one, no. Okay, because there's no symmetry within the molecule. If you had to say what's the proper IUPAC numbering system, you would know that you have to start here, 1, 2. You couldn't start here, 1, 2, 3. You wouldn't get to your alcohol until the third carbon. Okay. Here, no. Okay, there's no plane of symmetry in the two-dimensional structure. It's not palindromic. Clearly, you would number this one from the right. Here, yes, actually 2 of the diastereomers of this compound are going to be enantiomers. And this one, no, there's no plane of symmetry. Here, there actually is a plane of symmetry. It's a little hard to see. It's hard to draw a 10-membered ring because the bond angles are so wide that they don't look much like bonds, but we'll just go ahead and draw it anyway. But here it is drawn as a decagon, I guess. And here you can see that there is a plane of symmetry that goes right. Sorry, my aim was a little right there. And this is, in fact, a molecule that can exist, or one of its diastereomers can be a meso compound. What about this one? Well, this one also could have a meso compound. Okay, so half this molecule and this half of the molecule both look alike, and if you lined up the stereocenters in the correct way, there could be a meso compound. All right, here's an interesting case here. Is cis 1,2-dichlorocyclohexane chiral? All right, and how you answer this question depends on the conditions upon which you're examining the chirality. If you're examining it at room temperature, or if you're examining it in a very cold, at a very low temperature. All right, so first off, you'd probably say, all right, if one of those chlorines is axial and one's equatorial in the 1-2 relationship, you really cannot draw any plane of symmetry in this molecule. And if you look across the mirror, you see that. And there's no way to interconvert it. But there actually is a subtle way to interconvert it. That's to ring flip it. All right, so let's ring flip it. All right, we're going to ring flip it. And now rotate it this way by 120 degrees, okay? And when you do that, this is the molecule that you end up with. Okay, so here's our rotational axis here, going straight through the molecule. And this is where we're the way we're rotating it. All right, so do that rotation, and you end up with this. And what you see here is that if cyclohexane ring flips, or if cis 1,2-dichlorocyclohexane ring flips, it ring flips into its mirror image isomer. Okay, so therefore, if it's ring flipping, it's actually interconverting with its enantiomer, and thus it's not chiral. Okay, it would be a racemic mixture. Okay, but if you're examining it in a very cold environment where ring flips are extremely slow, it would be a chiral molecule. Okay? All right, so if you're asked whether a cyclohexane derivative is chiral or not, I know you don't want to, this is not a good thing to say because we've made such a big deal out of the chair, but if you just draw it as a hexagon, you'll get the right answer. And here's the reason, okay? Because it's undergoing a rapid ring flip, the hexagon is kind of like the averaged conformation, okay? So you just look for the planes of symmetry within the hexagon, just like we did with the cyclopentane derivatives earlier, and that'll tell you whether or not it's chiral at room temperature. It wouldn't show chirality, this type of molecule, the cis 1,2 isomer, would not show chirality unless there's something that's causing the ring flip to not happen. Okay, so here is the definition of enantiomers and diastereomers that will serve you the best. These are the most powerful, all-encompassing definitions. Enantiomers, yes, they're mirror image isomers and all this good stuff, but what you really want to concentrate on is that they have the opposite configuration at every single chiral center, whereas diastereomers have the opposite configuration at least one, but not all chiral centers. Okay, I call these EDI problems because on the exam I ask you to write E if they're enantiomers, D if they're diastereomers, and I if they're identical compounds. Okay, so let's go through these compounds here. This is a very common type of exam question. Two compounds written from different perspectives. Are they the same compound? Are they diastereomers? Are they enantiomers? Okay, One of the worst answers I always get here is a compound with a single chiral center. Somebody will tell me it's a diastereomer. That's impossible. It takes at least 2 chiral centers to make a diastereomer. So I don't want to see anyone tell me that that 2 compounds that have only 1 chiral center are diastereomers. Okay. They have to be either enantiomers or identical. Alright, so let's look at these compounds. We'll look at just a few of them on each slide. The top one. What are they? The most reliable way to do this is to assign the R and S configuration. You can sort of see that these are mirror images, right? So they're probably enantiomers, and it turns out that they are. The one on the left is the S enantiomer. The one on the right is the R enantiomer. They're mirror images of each other. Okay? All right. What about these next two? Well, here, let's see. Are they mirror images? No, they're not. But what you can see is that they have exactly the same perspective of the cyclopentene ring, but they have the opposite configuration here at their only chiral center. Therefore, they would clearly be enantiomers. Okay, one would be S, one would be R. And if we just flip this one over, they would look exactly like the previous problem. All right, let's look at these next pair. Okay, again, this is in the same perspective. We have each of these being opposite at every chiral center. At first glance, it may seem like they should be enantiomers, but this is kind of a loaded question here because these are Meso compounds. Okay, they are not enantiomers, even though they may look like it. Okay, so what you could do here, realize, is that you could just take, let's say, flip it over on this axis and turn one of them into the other, and you would generate basically the same compound. So these are not enantiomers because they're Meso compounds. Okay. If there was something in them making them different, if this plane of symmetry didn't exist, then they would be enantiomers, but because they're Meso compounds, they're not. All right, let's look at these two. All right, many of you probably realize that if I just flip this sucker over, it would become that one, right? And thus, these are identical compounds. And again, the S and S relationship between the two chiral centers also ensures that they are identical compounds. All right, what about these two? If we go here to here, they're opposite. If we go from this chiral center to this chiral center, they're the same. All right. There's also no possibility for this compound to be a meso. And thus, if they're different at one chiral center but not the other, they have to be diastereomers, different at least one but not every chiral center. Okay, let's look at this one here. Okay, opposite. And what about here? Hydrogen's the same, but we've intercalated converted CH2OH and ethyl. These are also opposite. Alright, so they're different at every single chiral center. There's no possibility of it being a meso compound. Thus, these are enantiomers, different configuration at every chiral center. The last one is a Fisher projection. But we do the same analysis. We look at each chiral center and see if it's different. Alright, so what about we go from here to here? They're opposite. We go from here to here. They're also opposite. Okay, notice how we keep the same vertical array of substituents. We're just changing the horizontal. Alright, there's not enough symmetry in this compound for there to be a meso compound. Therefore, if two compounds are opposite, they have to be, or if they're opposite at every single chiral center and there's no possibility of a meso compound, they are enantiomers. Okay. Alright, let's look at one other issue. That's enantiomers. We've described how they're identical in nearly every one of their physical properties, thus they're very difficult to separate. Diastereomers, however, have some a lot more differences in their physical properties. There's usually slight differences in almost all of their physical properties. Diastereomers often have different melting points, different boiling points. Okay, they interact with a separation medium in organic chemistry, silica gel, very differently. Okay, the separation of enantiomers is called a resolution. And it's a very difficult operation to perform. Basically, almost every one of the resolution methods involves temporarily making a diastereomer. Okay, so let's say we have this simple amine here, racemic. Okay, this is actually fairly easy to resolve into individual enantiomers. What you would do is you would react it with this carboxylic acid. Okay, so the amine is a base, the acid is an acid, and we're going to form a salt. Okay, since this is racemic, it's of course R and S, but this is only one. So the two salts that we form, we'll call this salt the the SR salt, and this salt the RR salt. And what you see here is these salts are diastereomers, and it turns out that they have different melting points, and you can recrystallize these compounds. Takes a little bit of skill, actually quite a lot of skill to do that, but these are quite readily resolved simply by recrystallization. Okay, so once you've got the salts separated, you can just treat this with base, and this will remove this extra hydrogen here and get you back to the free amine. And the free amine that you have here will be the S enantiomer. The base is going to keep this as the salt, and you can usually wash that away because that's very water soluble. Whereas this salt here is going to, after we treat it with base, is going to provide this ammonia derivative or amine as the pure R enantiomer. Okay, so this is one method of resolution. Okay, there are many ideas about, or many methods, but again, almost all of them rely on the fact that you create something that's diastereomeric and then turn it back into the enantiomer later as the basis of the separation. Okay, we're going to end this video with a few more problems. All right, so let's look at this one. For each reaction process, perform the following task. We're going to do these one at a time here. We're going to draw all of the likely products, describe the relationship between the products, and describe the relationship between the specific rotations of any isomeric compounds. We also should remember to spell between correctly. Okay, all right. So let's look at the first one. Mercuric acetate water followed by sodium borohydride. This is just going to be our Markovnikov alkene hydration, right? All right, so this original stereocenter is not involved in the reaction. Thus, it will not change. Although we have the possibility with two chiral centers of producing as many as 4 different stereoisomers, we only actually produce 2 stereoisomers, okay? We produce compound A and compound B. Compound A and B are diastereomers, again, because they are the same, one of them, but the opposite at the other. Okay, this stereocenter here is kind of far away and it's not part of a ring, so it's not likely to have much control over which side what OH adds from. So it's very likely that we're going to get pretty close to a 1-to-1 mixture of A and B. All right, what if we know that the specific rotation of A is plus 60 degrees? Can we say anything about the rotation of B? Actually, you can't say anything because A and B are not enantiomers. They're diastereomers. Is it possible that a mixture of A and B could be optically active? Yes, it could be because they don't have the same specific rotation value. Okay, so they won't perfectly subtract. Okay, let's look at the HCl addition. This is a little different because although we have 2 diastereomers like we did before, again, we're not going to change anything here. It's not affected by the reaction. We make C and D. Okay. But C actually is optically inactive because it's Meso, whereas D is the DL, or the chiral one. But it would exist as a single enantiomer, right? All right, so again, D probably has a specific rotation that's not 0. C has a specific rotation that is 0 because it's Meso and optically inactive. Okay, but we can't really do any, we can not make any predictions about the specific rotation of D. Okay, if C and D were mixed, there'd probably be some sort of optical rotation because they would not subtract perfectly. C has a rotation of 0. D has a rotation that's not 0. Okay, and C and D are diastereomers. They're not enantiomers, so therefore their rotations don't subtract perfectly. Okay. All right, let's look at another problem here. There are 4 hypothetical isomeric forms of 2-butene that can arise from the following reaction. Only 2 of them are observed. Which 2 are observed and why? A question like this, of course, most of the credit would come from the why because we have a kind of a high probability of knowing nothing and getting one of them correct, right? All right, so we're only going to be concerned with the 2-butene that we produce, not the 1-butene. Okay, so this is obviously a single enantiomer and a single diastereomer. All right, so what we remember about this is the E2 reaction, and we have to have hydrogen and bromine, or deuterium and bromine, if deuterium is going to be eliminated, perfectly anti to each other to do the E2. All right, so let's look at this molecule in its Newman projection. All right. All right, so we have to have a hydrogen or a deuterium anti to bromine to do the E2, right? All right, so this molecule that we have here actually has, if we call this the front carbon, okay, actually has hydrogen and bromine anti. Okay, another conformation that can do the E2 is this one, which has deuterium and bromine anti. All right, so let's go ahead and do the E2 here. And remember, our base is going to come along, pull off the proton. We're going to form a double bond, and we're going to eliminate like that. Okay, notice here that in this conformation, methyls are on the opposite side. So this is going to give us the trans. And here methyls are basically very similar on the same side. They're gauche here. And this conformation is going to give us the cis. All right. So we're going to get the trans is going to have deuterium. That's B. And the cis that we get is not going to have any deuterium. So that's going to be C. All right, we're probably going to see a lot more of B than C because of the kinetic isotope effect, right? The hydrogen's more reactive than the deuterium. It's also likely that the conformation on the left is a lot more stable than the one on the right, so we're going to see more of it for that reason. But we should not see any of A and D. We should see only B and C, but a lot more B than C. Okay? All right, so I think that's where this video ends. I'm going to have one more where I'm just going to be showing you how some of these things superimpose.